Hello, welcome to Hazard Factory. My name is Rusty Oliver. This is the next item that is going into the crate. This is what we've made to test not only the armor, but a shock mount, and this core is ultimately just representing the weight of the robot. So this is the next article that will go into the Combat Robotics Armor Test Environment.
Hi, I'm Yasha. I'm with Machine Core, and we're here talking about armor. Right here you see a piece of 1/4 inch thick AR-500 steel from which most of Chomp's armor has been cut. We and a lot of other teams believe that AR-500 is a good armor in BattleBots, and the general school of thought is that it is both hard and tough. Exactly what makes good armor is debatable, but if it's tough, that means for sure it takes a lot of energy to remove a piece of the material. And if it's hard, then you think perhaps that a sharp weapon won't get as good of a bite when they engage. We're hoping to prove with the crate that perhaps things that are tough but not so hard, like composites, might also be good armor. Chomp's armor consists of 3 pieces. The top shell is titanium. The lower section is the AR-500 steel, which is quite difficult to bend, but possible. This is a 3-inch bend radius here you see in the front. And the front 2/3 of the robot is a single piece that comes all the way back to about here, where it's joined to the rear piece. In case of extremely violent enemies, we have another wrap that wraps around. So this is the double layer that we use on the front of Chomp when fighting spinners. You can see it's suffered some combat damage. After fighting a few robots, we decided we weren't going to run this anymore. We needed the extra weight for other parts of the robot, and it didn't look like the opponents were about to get through this layer. We designed a bender basically from whole cloth. It shares a lot of similarities to a tubing bender, where you clamp the piece you want to bend to a static reference, and then you use a roller to roll it around a mandrel.
Hello, my name is Dmitry Vasilov. I was part of Team Chomp, part of the Machine Core, and I helped build the bender. So why do we need a bender? Well, it turns out that welding steel, specifically AR-500, is a really, really bad idea because you locally temper the corners of where you welded, and that creates weak points. And so you can imagine if you get hit really, really hard on that weld, it's probably going to break. We really want to have nice, strong bends instead. And so this is why we built the bender. We have our main tombstone that's bolted to the ground. It's super rigid, torsionally rigid. We have our clamping surface right here. You have your bending die, which in this case is just a nice, smooth 2.5-inch radius water jet pieces right here. This is the roller that we're bending around the die. The art of bending is a super magical thing, which we don't really understand. We took our best time of calculating all different parts associated with it, such as the bend radius, the material thickness, bend start point, etc., etc. And we got pretty close, but we unfortunately drastically underestimated how much force was required to bend AR-500. And so this was our best guess here, which is a 5-foot lever arm. But in reality, we actually need a forklift to move it, which is very humbling.
We had to drive the forklift against this end of the arm. So we don't have any control at all. And so once you have your piece clamped here, sticking out into the room, you then drive this around, not to 90 degrees if you need a 90-degree bend, but because this material is so strong, you bend it to about 140 degrees, maybe 50 degrees of overbend, and it springs back from that to 90 degrees. That took a lot of experimentation to get right. This piece is the correct size. The bends bring these 2 faces to the correct dimension, but that was definitely not the case with the first piece. The piece that you see tested in the crate is our first article that we had quite high confidence would be wrong. We bent it to the nominal bend lines, and then we measured how wrong it was, and then we just corrected our bend positions by that error. So this is the first piece of armor we bent. It's a perfectly good piece of AR-500 that we can use to test the effectiveness of this armor in the crate. So the plan is to mount it to the front of this wooden buck, and This is to simulate the way we like to design armor on our BattleBots team. We don't like to mount the armor rigidly to the rest of the robot. We like to mount it with a little bit of shock isolation. So this piece of AR-500 will be bolted directly into this piece of wood, which is not too heavy. But the bulk of the mass of this system is in this steel weight stack here and this base plate here. It's about 200 pounds of steel. We're going to fill this annular gap with Shore 60A hardness polyurethane, which is similar to the hardness of the shock mounts we use between Chomp's chassis and her armor.
Okay, and that should be our weight. The idea here is to remove this weight stack so that we can get it into the container. We have to wrestle it through kind of a corridor. And I've got a lift magnet on all of the weight. With a little bit of luck, it'll pull right out. And it does not. The most recent thing here is that we've attached accelerometers, which are hooked up to an Arduino stack up here. What we intend to do is generate data from how quickly these are accelerating, and then we can cross-check that data against how quickly this is decelerating.
This is the buck and the weight stack mounted to the sled, and these two little ICs here are accelerometers that hopefully will gather data about the force of impacts hitting this buck. But here's the thing. Measuring hard things, hitting hard things is diabolically difficult because the forces get really high really quickly. Here's a couple of examples. When Jamie and I got our first crash test dummy, we thought this is robust and made for horrific impacts. And we found that the average crash imparts about an average of 70 Gs, 70, 80 Gs of force on the human body. So we took Buster to the top of this crane and we dropped him 170 feet into water, and we blew up the accelerometer because we exceeded its 500 G limit. We were somewhere way over that, just dropping him 170 feet into water. And the way to think about it is the impact of a hard thing into a hard thing creates a very, very powerful force in a very short period of time. And you can kind of hear it if I do that. You can hear how sharp that sound is. But if I give a little bit of strain relief to that sound, a little bit of padding, you can hear, right? One graph you can picture as a sharp point and the other has a little bit of a flat plateau on top. Well, that is why this accelerometer mounted hard to the buck often is exceeded and doesn't give a reading, whereas this one, buttressed between the Shore 60 hardness buffer here, actually does give a reading. And by cross-correlating that with the rotational forces and stuff, hopefully they'll be able to get a genuine reading on how much force is involved in the impact.
This is the moment we've been waiting for. The crate's weapon is up to full power, we have the pneumatic sled dialed in, and we have the telemetry and cameras up and running. Now we can actually do some tests with a 250-pound fake BattleBot test mass of some materials that actually could be real BattleBot armor. Namely, we're going to test AR-500 steel that we've used in the past. We're going to test Kevlar to see if that could be a good alternative. And then just for fun, we're also going to test some 1/4-inch mild steel.
Turn that camera on. Turn that camera on. Okay, we're gonna get this data recording. Okay. Got everything recording. All right.
we were more or less expecting it to get tossed, thrown, and mangled, and instead what we saw is it hit in such a way that it shed the bulk of the impact of the blade. The blade carved a big groove in the front of the armor, but it didn't catch enough to actually toss it and damage it the way that we were expecting. This is actually got some deformation now. And after everything that we've fed into it so far, this is the first time that we've actually seen any kind of movement in the blade. This is chipped away a little bit. We fed it a server, a microwave, and several fire extinguishers. None of them have thus far done anything to affect the geometry of the blade. And now we're actually seeing a little bit of movement.
If you've watched the other crate test videos, you might have seen the AR500 test and thought, huh, not very dramatic. That's because AR500 really is good armor, and we saw it do its job. If you look at the armor, it got maybe a 1/16 of bite at the most, but it was hard enough that it didn't let the S7 tool steel blade really bite in and impart a lot of energy. Instead, it skidded backwards and it made this dramatic shower of molten sparks, but other than that, it didn't really affect the bot that much.
So what we're doing now is presenting different pieces of material to the blade. The first one we did was the AR500, and we showed you the result of that. What we're going to do next is present this piece of mild steel to the blade. We've got a pretty good idea of what's going to happen here. It's not going to be impressive. The mild steel is going to get more torn apart than other samples. The Kevlar, this will be a really interesting test. We haven't put any Kevlar to the blade yet. It's going to present in the same place, roughly the same fashion. Well, I mean, actually exactly the same way. And we're changing the blade because we noticed this tiny little deflection in the surface of the blade. This one's a little more severe. And so, having lost this corner, we want to kind of do a control where by flipping the blade, we're presenting a sharp corner to the Kevlar and the mild steel as well. Just about set. So we've got 1/4 inch.
Wow.
Oh my God. Wow. It hit hard enough that the oxide all popped off of the backside. Like we were noticing smaller chunks on one of the impacts before, but I think that's a shaving that came off of the face and ended up embedding there, because we can see the bluing. Here's one that's stuck in the wall. And this is a little shaving. It's kind of wedge shaped. This is really interesting. Look at the exit on this side. It almost looks like a shell. It's like kind of, see how these little, it's
scalloped.
Yeah, it's like this edge is like scalloped. Like you can see it better on this side. It's like a saw blade almost. It's in there pretty good. Alright, so that obviously went in with a good bit of velocity, and this upper edge has a really interesting looking tear to it. I'm going to try to get a little wood out of the way. And the lower edge is clean, and the entire thing is shaped like a wedge, with this edge being the thicker, this is the narrower.
That's hard to conceive how much power is going on. I love that it's like softened it enough that you see the blue. Oh my Lord. What's amazing is that there's artifacts to it that make it look like any soft material that you would shear or cut in this way, except that it's fucking steel. But the cleanliness of that shear, such a crisp edge. This is like, if superheroes existed, this would be like the aftermath of any given fight. There'd be all this weird detritus that you, wow, look at what Superman can do with his eyes. But it also looks like if Superman was a whittler. Just sit there with some diamond blade.
Yeah.
Peel that out.
Yeah, exactly.
Kevlar is a lot less dense than steel, so we can use a greater thickness of it without busting our weight budget. Our test article is about 1 inch thick. It's made of about 100 layers of Kevlar, laminated together with epoxy resin, using the resin infusion technique. We've mounted this into a welded steel frame just to give us a way to bolt it onto the wooden buck.
Here I'm about to weld a couple blocks together to hold the Kevlar to a piece of mild steel. This is just to present the Kevlar to the blade properly. It's a mount. Broke my welds. I'll have to call upon my MIG welder and Shane.
So this is the result of the Kevlar test, and I think we've officially decided that the armor needs to be both tough and hard. And some of this might come down to how toughness is measured in the engineering world. The test that determines it does not use a cutting edge, it uses a blunt edge. And so even though this Kevlar, by the data sheet, has a similar toughness to the AR500, it was really destroyed by the test. The test article is cut almost all the way through. You can actually see failure on the other side of the test piece through 1 inch of armor, whereas the AR500 only probably experienced about 1/16 of an inch of penetration. So there you have it.
There's a thing that they talk about on Numberphile that, like, at the high end of the mathematical spectrum, when numbers get big, stuff gets weird. And I thought of that when you said, at these speeds and this amount of force, stuff gets peculiar.